Hey guys, today let's talk about maximum width of a binary tree. This problem seems very simple in the beginning, but it actually took me a while to actually figure this out. So I have a binary tree right here. So the problem statement is at each level, at this level, let me choose. Okay, at this level, what is the width? It's 1. At this level it is 2. At this level it is 4. Okay, what is the maximum width in a given binary tree, right? This is a full binary tree, meaning all the nodes are completely filled with values. So here we don't have a problem, the maximum width is always at the last. But imagine a tree with something like this: A, B, C, D, E, missing the inner branches, F, G, something like that. Imagine something like that. Now what is the width, right? Ideally, our common sense would teach something like, yeah, at any point, whether it is this is here, it is 1, here it is 2, here it is 2, here it is 2, the maximum width is 2, right? But the problem is not that simple. The problem what he's saying is you have to consider the missing branches here. So what are the missing branches here? Let me denote in red pen. Is I have a null here, I have a null here. So the width here is 4. I have a null from this one, because this one and this one are null, they obviously do not have any more children. Then I have a null coming from the E, and from D. Here also the width is 4, and the 4 is the maximum width. Okay, so let me give you one more example. Switch back to purple pen. Imagine A, B, C, D, E, F, let's call it G and H. Okay, now the maximum width at this, let's calculate what's the maximum width. Here it is just 1, here it is 2. The missing nodes from this one are, there is a null here, there is a null here. So basically 4, 1, 2, 3, 4, and this one doesn't have kids, this one has 1, 4, again 4 is the max width. You can take this example and run it through several cases. You have to consider nulls provided that the parent actually misses its own one of its children, right? Now how to calculate this? The intuition is actually very simple. You would think that you would take binary breadth first search, breadth first search, BFS, and calculate what is the size at each level, and you can find out what the max width is, and that is a very good approach. But let's consider that. So if I take a queue, for BFS we always use a queue which is breadth first search. You always consider a queue, right? Now in your queue, what are you trying to put? Are you trying to put a node, or in LeetCode's term it's called a tree node? Are you trying to put the tree node? Is that good enough? If you put a tree node, what will happen here? Let me erase these red lines. Okay, let's go back. Sorry. Now If I put just a q, what will happen at this stage is that, see, whenever you add a q, you're not trying to you cannot calculate these missing characters. So switch back to red pen. You cannot calculate this null values here, cannot calculate the null values here, cannot calculate the null values here, because how would you ideally calculate the q is basically you can add a q of tree node, okay, and the pseudocode is very simple. So you can just say q dot add root, and while q is not empty, you will take the current size of it, which basically int size is equal to q dot size. Then you'll loop over the size, and you will say you'll get the current node, which is using q dot poll. You are taking the latest element, which is the topmost element from the queue, and if current dot left not equal to null, you are going to just say q dot add current dot left, and similarly you will do it for right as well. Okay, now where are you actually calculating this width? The width calculation must come around here at this point, right? At this point, because here that where the level switching is happening, meaning first in my queue there is a, I denote a with a circle around it to denote that it's a tree node, not just a value a, right? First I have a, then I take a out. Okay, now the level has complete, which is at here I detected the size, which is of size 1. Now if I put something like max width is equal to math dot max of max width comma size, will that be enough? So let's check, right? So we'll see what the size is, what the max size is. So the size is basically 1, max size is basically 1, 2, right? And you're trying to see whether you have left and right nodes. So basically, yeah, I do have left and right nodes. So adding B, I'm adding C at this stage, and by the time I go back here, the size becomes 2, because now you have completed this for loop right here, and you are switching to the next level. When you are switching to the next level, the size becomes 2, the maximum size becomes 2, and because you polled B out, you are going to add D. There is no right child to B, so basically you don't add anything, and then you poll C out, then you add a right child of C, which is G. Actually, let me erase it, sorry, and we'll add G back. And at this stage the queue size is still 2, and max size is also still 2, but the immediately, because the here at this stage we know that you have to consider null values. For you to consider null values, you just cannot say, if you just cannot remove this line when you are checking this line, you cannot do this, because what will happen is these null values will throw you a null pointer when you are trying to do current dot left next time. Let's say I add a null value here, D instead of G. If I add a null value here, then null value again from this guy, and then G, what will happen when this null encounters? you will get a null pointer here, right? If I'm going a little fast, please rewind and make sure you understand this concept, right? You just cannot keep adding null values here, right? So the another way of thinking is basically, see, the null values are being calculated only when there is a leftmost point and a rightmost point, right? So let's look at a different example. Let's switch back to purple pen. Let's look at different example. A, B, C, D, and G. Now this is interesting. Now we'll determine what the width is. Here it is always 1. It has 2 children. It is 2. Now here what are the null values? There is a null value here. There is a null value here. But is it really 4 though? Is it really 4? No, because the leftmost node is here. That means you do not consider this in the width calculation. A width calculation is distance between leftmost and rightmost. What is the leftmost? D. This is the denoted by LM. G is the RM, and the missing nodes in between is just 1. Therefore the answer is 3. You get it? So net we need to find out what my leftmost element is and what my rightmost element is. Once you determine that, then you can do subtraction and do all that, and you can figure this out. So I got this idea fairly quickly to actually determine this leftmost and rightmost, but the devil is in the details, right? So let me draw this again, right? Let me draw a complete full binary tree. Now if I start indexing these nodes, something like so, I'll do it in like I don't know, brown pen. 1, so at any stage, if I know what the index of the each node is, I can probably subtract, right? So here it's always 1, so it's always 1. Don't worry about it. Here 3 minus 2 is basically 1, but the width is 2, right? So let's add 1 to this. Here, will the addition of 1 be sufficient? Let's look at that, right? 7 minus 4 is equal to 3, but the width is actually 4, so you still have to add 1, meaning the formula is formula for width is equal to rightmost index minus leftmost index plus 1. Okay, fair? Okay, good. Now next question is, how do I find the rightmost index and leftmost index? This is also fairly simple. Now you can see a very simple relationship. So the node ID here is 1, or the index is 1, here it is 2 and 3. So that means this relationship is, if I call this as an index ID, this is 2 into ID, this is 1 plus 2 into ID. Same thing, here it is 2, this is 2 into ID, which is 4, this is 2 into ID, sorry, 1 plus 2 into ID, which is 5, right? So the index calculation is also fairly simple. Now let's see, if the index calculation is also fairly simple, how, and we are still sticking with BFS, how do we get that information? Net, if you think about it, you don't you along with the node that you are supposed to get from the queue, you also need the id, because based on this id you are calculating whether you have left id and right id and all that, right? So that's the key. So your queue immediately becomes, your queue has to store an combination of the node and the index. Okay, and I wrote the code in such a way that it's basically a pair of integer which is denoted by index and the tree node. The tree node is denotion from the lead code. I call it node in general terms, and yeah, that's it. So that's the queue I created. Okay, that will be my queue. Now initially I will add queue dot add of new pair of something like 1 and root. Oh, sorry, not these brackets but the parentheses. Okay, and that's what it is. And I would just keep on adding, and I would still use the same logic. It's rotated around the size, and I am adding if the current is null. So I am considering, okay, you know what, let me write it down again, so not a big deal. So here while queue is not empty, okay, what will I do? I'm going to get the size of it, size of the queue dot size. Then I'm going to loop around this size for size, something like that, just for loop. And I would get instead of getting a tree node, I'm probably getting a pair. Current pair is equal to queue dot poll, right? And so the current tree node is equal to cp dot get value, and current id is equal to cp dot get key. Okay, and once you get this information, what am I going to do? I'm going to add this queue dot add. When am I going to add this? If I'm gonna call this current node. If cn dot left not equal to now, wanna say new pair of current id, which I'll say cid into 2 comma cn dot left and q dot add if cn dot right not equal to now, q dot add, and I will add a new pair of cid into 2 1 plus comma cn dot right. So far we are adding all these information properly. Okay, so far we have achieved, what did we achieve is basically we know how to calculate the IDs, indexes, we know how we are switching the levels by levels. Now the last thing we need to do is the formula of the width. Here the formula of the width would be, so I would say like max width is equal to math dot max of, max width comma, So now where is the leftmost index and rightmost index calculation? We did not do that, right? So that is the crux of the problem, obviously. That's why we are doing all this nonsense, right? So anyway, how do I find the rightmost index? Rightmost index should be ideally the last current ID, correct? Meaning here when you are at this level, C is my latest and greatest or the rightmost node, and here G would be my rightmost node. So if I can capture this current ID, so I'll switch the pen color here to red. So rightmost will be current ID, right? There is no question about it. That's what the rightmost node is. Then what about leftmost node, right? What is leftmost node? Leftmost node is nothing but when I'm switching the level from here to here, right? This is my leftmost node. Meaning when I try to switch in the queue, whatever is the 0th element, that is my leftmost. So I can add here in leftmost is equal to q dot peak. I don't want to get it out yet because all the polling and all this logic is still here. I'm not disturbing that logic, but I'm just trying to get the peak, and I'm gonna say get key. The moment I do that, even before going and polling it out and trying to do another math.min and all that logic, I can just directly determine here, okay, at this level, what is my leftmost node? Here the D could disappear and easily the E would become the leftmost node, because by the time the queue's 0th position is this. C is already processed because it's outside the for loop, and you would have handle on the E. So the leftmost is very simple. The leftmost calculation is, let me minimize this, right there. All right, so here I would just say rightmost minus leftmost 1 plus. Finally I would return max width. Okay, I hope this makes sense. Again, this calculation of the, I'm gonna highlight this in yellow, this calculation of the leftmost and the rightmost here is what took me the most of the time. You know, I was able to quickly come up with the logic of, oh, how would I calculate the width, how would I calculate that width, and indexing each node. I came up with this logic actually fairly quickly, I don't know, in like 7-8 minutes. But this calculation, while I was coding it, it took me the longest, because the leftmost node, even if you have some kind of a minimum maximum value set within this for loop, it's not going to sit correctly. And the determination of the rightmost node also took me a little bit. I worked over 45 minutes to about 1 hour on this problem. But yeah, this is a good problem. It's just the concept of where to find out that leftmost node and rightmost node is critical, especially for me. But I think once you have the idea of finding out the indexes and finding out this formula, then I think it's fairly simple to implement. So yeah, the code again is on GitHub, so please check it out. If you find any corrections or anything, Please put it in the comments and I'll be happy to respond. Thank you guys.